Okay, two last series because, like I said, 8 isn't enough. Two last tests, I should say. The first one is the ratio test. And it's good for things that have factorials and stuff like that in there. Because factorials are kind of a pain to deal with in the limit comparison test, and there's certainly a real pain to integrate, things like that. So we'll start with the ratio test. We're going to assume that we have some terms that have a limit of 0, or a limit that's less than 1. And if these terms have a limit that's less than 1, then we have a series that's absolutely convergent. If we have a term that's, this looks a little odd. I think I've screwed up. This isn't the ratio test. Man, that's a bummer. For the ratio test, yeah, I just copied the wrong thing there. My bad. I'm glad I caught that. I was looking at that going, wait a minute, that's the root test. For the ratio test, we want to take a look at the limit as n approaches infinity of a sub n plus 1 over a sub n. If that limit, whatever that is, let's call it L, if L is less than 1, then the series converges absolutely. So if L is less than 1, this series converges absolutely. If it's greater than 1, what do you think happens? Yeah. If L is greater than 1, the series diverges. Series diverges. And last but not least, if L equals 1, what do you suppose happens if L equals 1? Yeah, it's inconclusive. Okay. Now you can do a similar thing with the, so this is the ratio test that I had to kind of ad lib here because I actually copied the root test twice. The root test, you're going to do something kind of similar to that. You're going to look at the nth root of these terms. If the limit of the nth root of these terms is less than 1, the series is absolutely convergent. So this is for your root test. Less than 1, it's absolute convergent. Greater than 1, it's divergent. And equal 1, it's inconclusive. So similar kinds of conditions. It's just you're dealing with the different expression that you're taking the limit of. Let me start with, let's see. Let's start with this one right here. And we'll work on a couple of these things. We're going to start with example D here. So I apologize for not starting at the beginning. Example D. We've got the sum from n equals 0, which is interesting because you're not starting at n equal 1, but that's okay. Where you start is just going to represent a finite number anyways. 2n plus 1 factorial. Now, factorial, when I see factorial, I start thinking root test. Or not root test, but ratio test, because it's hard to work with these things with any other test. So let's look at the general term here. Our general term, a sub n, is going to be negative 9 to the n over 2n plus 1 factorial. Let's figure out what the next term looks like. Because to use the ratio test, I've got to look at the limit of the n plus first term divided by the nth term as n approaches infinity. So I want to calculate both of these. Now I've got a sub n. I need to figure out what a sub n plus 1 is going to look like. Is that showing up pretty good? Maybe I should use blue. N plus 1. Is that better? Yeah, I think it's a little bit better. So wherever there's an n, I've got to replace that with n plus 1. So for instance, I'll have negative 9 except I'll have it to the n plus first power. And then I'll have, instead of 2n plus 1 factorial, well, I'm going to play with that a little bit. I'll have 2n plus 1 again, factorial. Let's clean that up. If I distribute this, I'll end up with negative 9 to the n plus 1 over 2n plus what? Can anyone finish that up for me? 2n plus 3 factorial. Now let's remind ourselves real quickly about factorials. N factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1, etc. That's going to be your n factorial. We're going to do likewise with our terms here, but we're starting out at a much different expression. So we're going to apply the ratio test. The thing that's saying apply the ratio test is we got these ugly factorials. So let's look what those have to offer. I want to calculate the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n and I guess I'll write it out kind of at length for us this first time, but moving forward I'm going to kind of try and do this a little bit quicker. A sub n plus 1 is this term up here. Negative 9 to the n plus 1 over 2n plus 3 factorial. And then in the denominator it's just negative 9 to the n over 2n plus 1 factorial. Now when you divide fractions, you're going to multiply by the reciprocal. So I can rewrite that as the limit as n approaches infinity of this numerator term multiplied by the reciprocal of the denominator term. Now one more question for you. Take a look inside here. We've got some negative 9 to certain powers. Are those negative signs going to make a difference in the long run? No. Why not? Yeah, because we got the absolute value. Let me just get rid of those right away because they're getting kind of annoying to write. So thank you. So it's just going to be 9 to the n plus 1 over 2n plus 3 factorial times the reciprocal here, which is going to be 2n plus 1 factorial over 9 to the n. And so now I got to clean up that and work with that moving forward. Try and get a limit. Are we okay with the first couple steps here? Thank you for those nods. Appreciate that. Let's take a look at the limit as n approaches infinity of n 9 to the n plus 1 over 2n plus 1 factorial. Now here's where we got to think a little bit. N factorial is that number times that number minus 1 times that number minus 2, etc. I'm going to rewrite that factorial. It'll start out as 2n plus 3. But what's the next number down from this if you're putting in integers? 2n plus 2. and then 2n plus 1, but I'm going to stop it here. I'm going to write it as 2n plus 1 factorial. Can someone suggest a reason why?
Cancel it out.
Yeah. I've got a 2n plus 1 factorial up here that I can cancel out with. So that's the little tricky part, is rewriting this so that you get that massive amount of cancellation. I'll pause. I mean, think of putting in a number here like 2. This would be a 7. This would be a 6. This would be a 5. So you're just subtracting 1 from each to get from one to the next. All right, lots of nice cancellation here. Those whole terms go away. Is there anything else that can go away? Well, yeah, tell you what, let me redo this in a more user-friendly or student-friendly way. Let's write 9 to the n plus 1 as 9 to the n times 9 to the first power. When you multiply things with the same base, you're going to add their exponents. So that lets me get rid of this real quickly. What's left? Well, just a 9 to the first power over 2n plus 3 times 2n plus 2. Drum roll, please. What's that limit? 0. That's nice. It's equals 0, which is less than 1. Therefore, the series converges. How? Absolutely. By the ratio test. Nice. The ratio test is pretty cool. It makes some of these calculations a lot easier than they would be. I remember when I first looked at a factorial problem, I'm like, you're kidding me. But then they told me about the ratio test and I felt a lot better. So, okay. How was your first look at the ratio test? Okay. The big tricky thing here is correctly getting the n plus first term. That's going to take a little bit of practice and comfort. Tried to help you out by putting it in nice colors so you can see what happened with the n. The other thing is working with these factorials. Just a little extra care working with those too. But the series converges, so we're pretty happy. Let's try another one here. Let's try the next one over. Looking pretty similar, pretty different, I guess I should say. So that'd be example E. And we don't have a factorial in there, but we do have, a power. One thing you want to notice is that this is not a geometric series. The e to the negative k term could be a geometric series, but not when I've got a k in the numerator there. So let me rewrite this. That's going to be the sum from k equals 1 to infinity. I'm going to write it as 6k over e to the k. So I'm just putting that e term in the denominator, get it out of my way a little bit, get rid of that negative. So let's look at the general term, a sub k. 6k over e to the k. I want you to write the next term. So a sub k plus 1. Try and write that, see what you get. Oops. I don't want these here. you should get something like this. 6 times k plus 1 over e to the k plus 1. Since we're looking at the k plus first term, we're definitely going to be applying the ratio test. We want to look at the limit as k approaches infinity of the absolute value of a sub k plus 1 over a sub k. Do I really need the absolute value in this problem? No. No, everything's positive, so I'll skip that part. Limit as k approaches infinity. Now I give you a heads up on this on the last problem. As I do this, I'm going to have this term divided by this one. It ends up being the 6 times k plus 1 over e to the k plus 1 times the reciprocal of this term. So let's just put that in there right away. E to the k over 6 to the k, or 6k. All right. Lots of simplification here. Let's see if we can't figure out some of these things simplify to. I think right away you can see some of the simplification. For instance, the 6's disappear real quickly. What else can disappear? E to the k. So let's cross off our e to the k term here. And let me do it in blue. But that doesn't completely cancel out this. What's left in the denominator here? E. Just 1e, right? So let me just rewrite this. This is the limit as k approaches infinity of k plus 1 over e times k. Ooh. Who's good enough to spot that limit as is? Let me give you a little hint here. Yeah. You've got a 1, that's the coefficient of k in the numerator. You've got an e, which is your coefficient of k in the denominator. That limit is just going to be 1 over e. Yes, Hannah?
I have a question. For the first one, the e, or the 6 and then k plus 1, don't you distribute the 6 or be 6?
I kept it multiplied by this
Okay.
parenthesis. So yeah, I could do 6k plus 6, but in keeping it factored, I was able to cancel out the 6.
Oh, I see. Okay. That makes sense.
All right, appreciate that. Now the important thing, 1 over e is less than 1. So therefore, it converges absolutely by the ratio test. Nice. Nice. Let's take a look at example G. So I'll move up to this one here. So for example G, got the sum from n equals 2 to infinity. By the way, where you start really doesn't matter, because no matter where you start, it's a finite number of terms that you could be adding in or leaving off. So where you start really doesn't matter as long as this expression in the summons is defined. We've got negative 2n over n plus 1 raised to the 3n, like that. Now this one doesn't offer us any factorials, but instead what we do have is something to a variable power. Now this does not turn out to be a geometric series. You can take a look at the first few terms. You're not going to be multiplying by the same thing to get from one term to the next. But this does suggest, boy, it'd be really nice to get rid of that exponent there. And it does suggest the root test. Okay, looking good there. Let's apply the root test. So that's going back here or here, because I copied the same, my bad. Let's go here. We want to take the limit of the nth root of the absolute value of a sub n. So our a sub n, in this case, is -2 over n plus 1 to the 3n power. So if I want to take and calculate the limit as n approaches infinity of the nth root of this to, actually the absolute value of this, -2n over n plus 1 raised to the 3n. The absolute value is going to control that negative, so I'll look past that. And I'm going to rewrite this a little bit. Limit as n approaches infinity. The nth root of 3 to the n, those two operations are going to cancel each other out, as well as the absolute value of -2n is just going to be a positive 2n. So I'll end up with 2n over n plus 1 raised to the third power. Can anyone calculate that limit? Close. The inner part would be 2 cubed. There's a problem though, at least as far as the convergence of this series is concerned. What do you know about 8? Yeah, it's bigger than 1. Therefore, the series diverges by the root test.
Does it become a geometric series at that point?
It does not become a geometric series. No. If you list out a few terms, you can convince yourself pretty quickly you're not multiplying by the same common ratio to get from one term to the next. Yeah, so I appreciate it. So I backed off of this one in the last section. Let's see about doing it here and now. Because of the factorial, I'm thinking which test? Root test or ratio test? Ratio test. So let's work on this with the ratio test. And let me also take the time to remind you of something about relative growths. So relative rates of growth. There's kind of a pecking order. On the pecking order, your slow end would be the natural log of something. And then the square root of something. And that's smaller than, let's see, I don't want to put n to the n. Let me change this to an x. X to some power. And then after that, the next biggest thing would be a to some power. So exponentials. And then factorials. And then after that is n to the n. So those are, different rates of growth. This is really, really slow. This is, both of these last two are hyper fast. But what I wanted to get to in this part of it is that n factorial doesn't grow as fast as n to the n. N to the n just really takes off. It's a very fast growing function. So let's look at our problem here and try and decide what we think. What's going to happen here? Well, n to the n should grow faster than n factorial, so I'm guessing that this one's going to diverge, but we don't know. All right, let's go through and do the calculation. So this would be example H. Sum from n equals 1 to infinity of n to the n over n factorial. This one is kind of urging us to do the ratio test because of the factorial there. So a sub n is going to be n to the n over n factorial. Try and figure out what a sub n plus 1 is going to look like. Yeah, check with your neighbors, right? See what you get. So you should have n plus 1 to the n plus 1 over n plus 1 factorial. And let's see if I can't simplify that a little bit. Are we okay with this initial expression? All right. Let me rewrite this a little bit to see if we can't simplify it. I'm going to write that as n plus 1 to the nth power times n plus 1. Anyone suggest a reason why? Yeah, thank you, Brandon. Yeah, we're going to get some cancellation down here in the denominator. This is n plus 1 times n factorial. So right away, I can get some nice cancellation here with those two terms. So overall, that's going to leave me with n plus 1 to the nth power over n factorial. Not a huge thing, but a little nicer. You know, and in the end, we're going to need to be a little bit careful with simplifying this thing anyways. Okay, let's apply the root test, which means we're going to calculate the limit as n approaches infinity of a sub n plus 1 over a sub n, which for us is going to be this term multiplied by the reciprocal of this term. So I'm going to step down a little bit here. N approaches infinity. N plus 1 to the nth power over n factorial times n factorial over n to the nth. And it's nice that we simplified that a sub n term, a sub n plus 1 term. Why? What was nice about that? Yeah, thanks, Syed. Hasta la vista. Those things cancel. You're left with limit as n approaches infinity of n plus 1 to the nth over n to the nth. Which is the limit as n approaches infinity. I'm going to rewrite that. Both of these are to the power of n, so I'm going to write n plus 1 over n to the nth power. And I'm going to rewrite it one last time in the hopes that somebody might recognize this limit from Calc 1. That's going to be n over n, which is 1, plus 1 over n to the nth power. Does anyone recognize that limit? Kaiser. E. Well done. And we know that E is bigger than 1. So what's our conclusion? Yeah, diverges. Therefore, diverges by the ratio test. Whew. Nice. A lot of work on that one. But it's nice, though, that we can kind of look at these things and keeping in mind our little pecking order. We say, oh, well, factorial doesn't grow as fast as this. If this is in the numerator, then we probably expect it to diverge because this is going to be growing a lot faster than this. And that's exactly what happened. Had I written this upside down from what it is, if I had n factorial over n to the n, then that ratio would have been 1 over e, and then I would have been in good shape. It would have converged, but that's not what was written, so it diverged. Okay. I'm curious about this one, but you see, no, I think I want to do, is there one more that, no. Yeah, it looks like really the only one that looks good for the root test is this one. We can try a root test on this one. I'm not sure what to expect. I think the root test might work there. We'll see. We'll see. Okay, so we'll do one last one. So this would be example C. So we've got the series from n equals 1 to infinity of -3 to the n over n squared. Okay. If we're going to apply the root test, then we need to keep in mind what a sub n is. So the root test is going to have us take the limit as n approaches infinity of the nth root of the absolute value of a sub n, which in our case is going to be the nth root of the absolute value of -3 to the nth power over n squared. This one might get a little bit messy. I need the absolute value of all this stuff in there as well. Now the part that works out pretty nice is in the numerator. We can rewrite this as the nth root of 3 to the n, taking the absolute value of that term, over the nth root of n squared. So the numerator simplifies pretty nicely. How's that numerator simplify? Yeah, it just becomes 3. All right, good. So the numerator becomes 3. Yeah, the denominator, I'm not so sure what's going to happen in the denominator. Limit as n approaches infinity of 3 over n to the 2 over n. All right, I guess this works okay. So as n approaches infinity, you'd have to apply L'Hopital's rule here, right? That limit is going to be 3 over the limit as n approaches infinity of n to the 2 over n. And you got a problem here. This is an indeterminate form. So you're screaming out to use L'Hopital's rule, but it starts to become a real long problem here to use L'Hopital's rule. So at that point, you can do one of two things. You can either use L'Hopital's rule, which would take a lot of work, or you can bail out and try a different test. Use L'Hopital's rule, and I'll put eventually. How come you can't use L'Hopital's rule right now? Yeah, it's not the right form. It has to be infinity over infinity or 0 over 0. That's what you can use L'Hopital's rule for. So, yeah, I'd bail out and use the ratio test. Cameron?
I'm just a little confused. Why isn't the answer just 0? I mean,
Because n is going to infinity. Well, the exponent is going to 0, but the base is going to infinity. So if you were trying to kind of put this in your head, what you're going to get is an indeterminate form, but it's not the one that you use for L'Hopital's rule. What you get in the denominator would really look like infinity to the 0 power. And it's tough to tell which of those is going to win. Something to the 0 power is 1, but it's harder to say that when that something is infinity. And that's what's happening when you let this go to infinity and this go to infinity. You're getting infinity to the 0 power. You look a little unconvinced still.
I don't know. I just feel like it could still be 1 on the bottom because no matter what.
It's not. If we had more than 1 minute left in class, then I'd show you. But I really don't know what. I think we are going to end up with something finite here. If you do this with the ratio test, you'll end up with. Let's see. If you do the ratio test, you'll end up with a limit of 3, which is greater than infinity, meaning that it's going to diverge. So by the ratio test, it diverges. And I'm sorry that I'm not showing it here, but the limit there, when you apply the ratio test, is going to be 3, so it diverges. Okay, that's it for today. Take a look at some of these problems on the back there. Try and look at them ahead of time for class for Thursday.